Today we're going to dive into the last topic of the year. Now be careful, I didn't say the last lesson of the year, but it is going to be our last major topic of the year. And the topic is logarithms. Log a what? Logarithms, often abbreviated logs. Now hold on there, Mr. Naylor. That name sounds pretty complicated. I bet this is going to be a hard idea. Well, if you understand the statement that 3 to the second power equals 9, then you can understand logarithms. You see, logarithms relate to equations that involve bases and exponents. Now, what I hope to really show you is how logarithms will help us to find an exponent. Maybe for a statement like 4 to what power equals 20. You see, logarithms open up a whole new world of solving for exponents. So, what exponent do you think you put on 4 to get 20? I'll give you 10 seconds to find out. All right, how did you do? 4 to what power equals 20? Well, what this requires is some careful calculating of some exponents. Let's take a look on a calculator. You see, first maybe we should think about what definitely is not true. There is no way that it's 5 because it's not 4 times 5, but that would be 4 to the 5, and that is way too big. That is definitely not equal to 20. What about 4 squared? We should know that that's 16, and 4 to the third, well, that's going to be 64. So what has to be true about this exponent? Well, it has to be between 2 and 3. Maybe it's right between 2 and 3. Maybe it's 2.5. I mean, I can have an exponent that's a decimal, sure, but it looks like 4 to the 2.5 is a little too big. So maybe it's 4 to the 2.3. Maybe it's to the 2.2. Maybe it's 4 to the 2.1. Well, 4 to the 2.1, now that's going to be a little bit too small. But we know that we're getting closer. We know that the answer has to be between 2.1 and 2.2. So maybe it's 2.15. That's 19.1.69. That's not quite big enough, but maybe it's 2.16. Maybe it's 2.17. Now that's getting closer, but that's a little bit too big. So what is the exponent that we put on 4 to get 20? Well, the reality is that it's a decimal. And depending on how many decimal places you go, maybe if you go to 2.161 out to 3 decimal places, you see that we can get really close to 20. Now, of course, it's a little bit too big, but at least to 3 decimal places, it's really close to the number 20. So it looks like our exponent exists. And again, to 3 decimal places, we could say that that exponent is 2.161. Now, here's the thing. That number is a logarithm. It's the log base 4 of 20. Now, I didn't expect you to know what exactly that means, but we're going to learn, and we're going to learn that the log base 4 of 20 is actually this exponent. It's actually this number 2.161. Well, we have a really fundamental but basic definition, and that is anytime you have a base to an exponent equaling a number, that can always be written as a log, saying that the log base b of a will equal x. Just take a look at it. It's the log base b of a will equal x. In other words, a logarithm is equal to an exponent. A logarithm is equal to an exponent. Now, as I said before, I don't expect that you have 100% understanding of this definition, but I would like you to start to notice that what's happening is we're taking the base and we're writing that as the base of the logarithm. I'd like you to notice that we're taking the exponent and we're saying that that's what the log is equal to. And there's only one other number that's left here, and of course that's the number a, and you'll find out that that number always finds itself in this position. So a logarithm is an exponent, and what we can do is we can take some exponent statements known as exponential form, and we can convert them to log statements known as logarithmic form. So here we have the basic statement that 3 to the second power is equal to 9. We all know that that's true. Well, we could also say that the log base 3 of 9 is equal to 2. And that is also a statement that is saying that if we take 3 to the second power, that will equal 9. You see, logarithms describe the same idea. Again, the idea is we can say 3 to the second power is equal to 9. How about the statement that 6 to the third power is equal to 216? Could you just take it and put the numbers in the new places? Try it. So how did you do? You would say the log base 6 of 216 is equal to 3. Now, I understand you might be saying, well, Ms. Naylor, I can rewrite the numbers, but what exactly does this mean? Well, just hang in there. This is just the first step in understanding logarithms. So again, we have a base 6, and that's the base of our log. A log is equal to an exponent. So 3 is what the log is equal to. And so we say the log base 6 of 216 is equal to 3. How about 4 to the 1/2 power? Now, I left this blank so that we could just talk one more time about how to do an exponent that's a fraction. Remember that when you see a fraction, that the denominator is the root. So this problem is going to end up being a square root. And remember that the numerator is the power. So this is going to end up being 4 to the first power. That is the square root of 4 to the first power. And so the answer to this would have to be 2. Now, what we also want to do is we want to write this as a logarithm. Well, remember, if the base is 4, then we will have the start with the log base 4 of 2, and it would have to equal the exponent. And the exponent is 1/2. So can a log equal a 1/2? Sure, because 4 to the 1/2 power is equal to 2. Now, we can also go backwards. We can take a log form and we can turn it into an exponent form. If we have a statement like log base 5 of 25 equals 2, that would mean that 5 to the second power equals 25. All we have to do is say so, and it's true. 5 to the second power equals 25. Do you want to try to go backwards with this last log statement? So you should be starting with the base. The base is 7 to the -2 power equals. Now, does it really equal 1 over 49? Well, if you think about negative exponents, you know that always makes you flip to get a positive exponent. And when we do 7 to the +2, we do get 49. So 7 to the -2 equals 149 is the same as the log base 7 of 1 over 49 equals -2. Now, at this point, you might be saying, okay, Ms. Naylor, I can change the form of these, but why do we need this? Well, to help you understand that, the next thing I want to do is try to get you to think like a log. Now, to think like a log is Mr. Naylor's kind of funny way of making you think about what a log is equal to. And so if I have the log base 9 of 81, that would be like thinking 9 to what power is going to get you 81. It's like thinking to what exponent do I raise the number 9 to get 81? To what exponent do I raise the number 9 to get 81? Well, of course, it would have to be an exponent of 2. So that means that this log is equal to 2. Let's think like a log for the log base 36 of 6. To what exponent do I raise 36 to get 6? To what exponent do I raise 36 to get 6? Now be careful, before you say 2, that would be like saying that 36 squared equals 6. But you're close. It involves a 2. That's right, it's going to be 1 over 2. It's going to be 1 over 2. So the log base 36 of 6 equals a half, because 1/2 is the exponent that I can put on 36 to get 6. Now, some of you might be ready to think like a log on this last one. I encourage you to do that. To what exponent do I raise 5? In other words, 5 to what power equals 1 over 125? Now, if you're thinking 3, you're close. If you're thinking 3, but the problem is that 3 would give us 125. I want 1 over 125. That's right, it's going to be negative 3. So that means that this log is equal to negative 3, because logs are exponents, and I would raise 5 to the negative 3 power to get 1 over 125. Now at this time, I want to give you an opportunity to think like a log, that is, to think like exponents. These 4 questions will kind of get you thinking in that log method, where you try to come up with the exponent that you put on the base to get the value. Go ahead, this would be a good time to pause the video, see if you can set these 4 problems up. Although if you're a little unsure, I'm going to go over the first one here, and then you can pause the video to try to get the remaining 3. So to what exponent do I raise 10 to get 1,000? That would be, of course, like thinking 10 to what power is 1,000. Now, the answer that you really want to put on this line is really just the number 3. And then if we want to write that as a log, you would be able to say that the log base 10 of 1,000 is equal to 3. All right, so how'd you do with the remaining ones? 3 to what power is 27? 3 to what power is 27? And of course, that's also the number 3. And if we write that as a log, you would say the log base 3 of 27, right, equals 3. To what exponent do I raise 10 to get 0.01? Now, this is a good problem to kind of think about what is 0.01, and that's the same as 1/100th. It might be good to even rewrite it that way, because then you can say 10 to what power? It's going to be a negative power, right? 10 to what negative power gives you 1 over 100? Did you say negative 2? That way we can write this as the log base 10 of 1 over 100. And remember, logs are always equal to exponents, and that's why this is equal to negative 2. This is interesting. 7 to what power gives you 1? 7 to what power gives you 1? Wait a minute. That's always going to be the 0 power. Right. Anything to the 0 power equals 1, which allows us to make a statement that the log base 7 of 1 is going to equal 0. All right, so logs are exponents. Now, right now, what I want you to be able to do is be able to convert between the 2 forms and to be able to think a little bit like a log, that is, to think like an exponent. We will keep building on this. Don't worry. You will feel like that there is a purpose for this, and we will find out that our calculator gets into this concept so that it can help us to find some of these exponents. But for now, you have these 10 homework problems along with the chart to fill out, and then feel free to check them with the selective answer key that I provided. Some of you might be saying, hey, Mr. Naylor, you never showed us how to use logs to get that missing exponent from the beginning of the period. Well, I'm going to show you more about it tomorrow, but as a sneak peek today, all you have to do is divide on your calculator the log of 20 divided by the log of 4, and you get 2.161. And that's all there is to it.